In fiber-optic communications, wavelength-division multiplexing is a technology which multiplexes a number of optical carrier signals onto a single optical fiber by using different wavelengths of laser light. This technique enables bidirectional communications over one strand of fiber, as well as multiplication of capacity. The term wavelength-division multiplexing is commonly applied to an optical carrier, whereas frequency-division multiplexing typically applies to a radio carrier. Since wavelength and frequency are tied together through a simple directly inverse relationship, in which the product of frequency and wavelength equals C, the two terms actually describe the same concept. Wdm systems. A Wdm system uses a multiplexer at the transmitter to join the signals together, and a demultiplexer at the receiver to split them apart. With the right type of fiber, it is possible to have a device that does both simultaneously, and can function as an optical add-drop multiplexer. The optical filtering devices used have conventionally been Italens. The concept was first published in 1978, and by 1980 Wdm systems were being realized in the laboratory. The first Wdm systems combined only two signals. Modern systems can handle up to 160 signals and can thus expand a basic 10-bit S system over a single fiber pair to over 1.6-bit S. Wdm systems are popular with telecommunications companies because they allow them to expand the capacity of the network without laying more fiber. By using Wdm and optical amplifiers, they can accommodate several generations of technology development in their optical infrastructure without having to overhaul the backbone network. Capacity of a given link can be expanded simply by upgrading the multiplexers and demultiplexers at each end. This is often done by use of optical to optical translation at the very edge of the transport network, thus permitting interoperation with existing equipment with optical interfaces. Most Wdm systems operate on single-mode fiber optical cables, which have a core diameter of 9 AA micrometer. Certain forms of Wdm can also be used in multi-mode fiber cables which have core diameters of 50 or 62.5 AA micrometer. Early Wdm systems were expensive and complicated to run. However, recent standardization and better understanding of the dynamics of Wdm systems have made Wdm less expensive to deploy. Optical receivers, in contrast to laser sources, tend to be wideband devices. Therefore, the demultiplexer must provide the wavelength selectivity of the receiver in the Wdm system. Wdm systems are divided into different wavelength patterns: conventional, coarse and dense. Conventional Wdm systems provide up to 8 channels in the third transmission window of silica fibers around 1550 nm. Dense wavelength division multiplexing uses the same transmission window but with denser channel spacing. Channel plans vary, but a typical system would use 40 channels at 100 GHz spacing or 80 channels with 50 GHz spacing. Some technologies are capable of 12.5 GHz spacing. New amplification options enable the extension of the usable wavelengths to the L band, more or less doubling these numbers. Coarse wavelength division multiplexing, in contrast to conventional Wdm and Dwdm, uses increased channel spacing to allow less sophisticated and thus cheaper transceiver designs. To provide 8 channels on a single fiber, Wdm uses the entire frequency band between second and third transmission window, including both windows but also the critical area where OH scattering may occur, recommending the use of OH-free silica fibers in case the wavelengths between second and third transmission window should also be used. Avoiding this region, the channels 47, 49, 51, 53, 55, 57, 59, 61 remain, and these are the most commonly used. Wdm, Dwdm and Cwdm are based on the same concept of using multiple wavelengths of light on a single fiber, but differ in the spacing of the wavelengths, number of channels, and the ability to amplify the multiplex signals in the optical space. EDFA provide an efficient wideband amplification for the C-band. Raman amplification adds a mechanism for amplification in the L-band. For Cwdm, wideband optical amplification is not available, limiting the optical spans to several tens of kilometers. Coarse Wdm. Originally, the term coarse wavelength division multiplexing was fairly generic, and meant a number of different things. In general, these things shared the fact that the choice of channel spacings and frequency stability was such that erbium-doped fiber amplifiers could not be utilized. Prior to the relatively recent ITU standardization of the term, one common meaning for coarse Wdm meant two signals multiplexed onto a single fiber, where one signal was in the 1550 nm band, and the other in the 1310 nm band. In 2002 the ITU standardized a channel spacing grid for use with CWDM, using the wavelengths from 1270 nm through 1610 nm with a channel spacing of 20 nm. Many CWDM wavelengths below 1470 nm are considered unusable on older G652 specification fibers, due to the increased attenuation in the 1270-1470 nm bands. Newer fibers which conform to the G652C and G652D standards, such as Corning SMF28E and Samsung Widepass, nearly eliminate the water peak attenuation peak and allow for full operation of all 18 ITU CWDM channels in metropolitan networks. The Ethernet LX4 10Gbps physical layer standard is an example of a CWDM system in which four wavelengths near 1310 nm, each carrying a 3.125 gigabit per second data stream, are used to carry 10 Gbps of aggregate data. The main characteristic of the recent ITU CWDM standard is that the signals are not spaced appropriately for amplification by EDFAs. This therefore limits the total CWDM optical span to somewhere near 60 km for a 2.5 Gbps signal, which is suitable for use in metropolitan applications. The relaxed optical frequency stabilization requirements allow the associated costs of CWDM to approach those of non-WDM optical components. CWDM is also being used in cable television networks, where different wavelengths are used for the downstream and upstream signals. In these systems, the wavelengths used are often widely separated. For example, the downstream signal might be at 1310 nm while the upstream signal is at 1550 nm. An interesting and relatively recent development relating coarse Wdm is the creation of GBIC and small form factor pluggable transceivers utilizing standardized CWDM wavelengths. GBIC and SFP optics allow for something very close to a seamless upgrade in even legacy systems that support SFP interfaces. Thus, a legacy switch system can be easily converted to allow wavelength multiplex transport over a fiber simply by judicious choice of transceiver wavelengths, combined with an inexpensive passive optical multiplexing device. Passive CWDM is an implementation of CWDM that uses no electrical power. It separates the wavelengths using passive optical components such as bandpass filters and prisms. Many manufacturers are promoting passive CWDM to deploy fiber to the home. Dense Wdm, dense wavelength division multiplexing, refers originally to optical signals multiplexed within the 1550 nm band so as to leverage the capabilities of erbium-doped fiber amplifiers, which are effective for wavelengths between approximately 1525 1565 nm, or 1570 1610 nm. EDFAs were originally developed to replace SONETSDH optical regenerators, which they have made practically obsolete. EDFAs can amplify any optical signal in their operating range, regardless of the modulated bit rate. In terms of multi-wavelength signals, so long as the EDFA has enough pump energy available to it, it can amplify as many optical signals as can be multiplexed into its amplification band. EDFAs therefore allow a single-channel optical link to be upgraded in bit rate by replacing only equipment at the ends of the link, while retaining the existing EDFA or series of EDFAs through a long-haul route. Furthermore, single wavelength links using EDFAs can similarly be upgraded to WDM links at reasonable cost. The EDFA's cost is thus leveraged across as many channels as can be multiplexed in the 1550 nm band. Dwdm systems. At this stage, a basic Dwdm system contains several main components: a Dwdm terminal multiplexer. The terminal multiplexer contains a wavelength converting transponder for each data signal, an optical multiplexer and where necessary an optical amplifier. Each wavelength converting transponder receives an optical data signal from the client layer, such as synchronous optical networking, SONET/SDH or another type of data signal, converts this signal into the electrical domain and retransmits the signal at a specific wavelength using a 1550 nm band laser. These data signals are then combined together into a multi-wavelength optical signal using an optical multiplexer, for transmission over a single fiber. The terminal multiplexer may or may not also include a local transmit EDFA for power amplification of the multi-wavelength optical signal. In the mid-1990s, Dwdm systems contained 4 or 8 wavelength converting transponders. By 2000 or so, commercial systems capable of carrying 128 signals were available. An intermediate line repeater is placed approximately every 80–100 km to compensate for the loss of optical power as the signal travels along the fiber. The multi-wavelength optical signal is amplified by an EDFA, which usually consists of several amplifier stages. An intermediate optical terminal, or optical add-drop multiplexer. This is a remote amplification site that amplifies the multi-wavelength signal that may have traversed up to 140 km or more before reaching the remote site. Optical diagnostics and telemetry are often extracted or inserted at such a site, to allow for localization of any fiber breaks or signal impairments. In more sophisticated systems, several signals out of the multi-wavelength optical signal may be removed and dropped locally. A Dwdm terminal demultiplexer. At the remote site, the terminal demultiplexer consisting of an optical demultiplexer and one or more wavelength converting transponders separates the multi-wavelength optical signal back into individual data signals and outputs them on separate fibers for client layer systems. Originally, this demultiplexing was performed entirely passively, except for some telemetry, as most SONET systems can receive 1550 nm signals. However, in order to allow for transmission to remote client layer systems, such demultiplex signals are usually sent to OO output transponders prior to being relayed to their client layer systems. Often, the functionality of output transponder has been integrated into that of input transponder, so that most commercial systems have transponders that support bidirectional interfaces on both their 1550 nm side, and external side. Transponders in some systems supporting 40 GHz nominal operation may also perform forward error correction via digital wrapper technology, as described in the ITU-TG 709 standard. Optical supervisory channel. This is data channel which uses an additional wavelength usually outside the EDFA amplification band. The OSC carries information about the multi-wavelength optical signal as well as remote conditions at the optical terminal or EDFA site. It is also normally used for remote software upgrades and user network management information. It is the multi-wavelength analog to SONET's DCC. ITU standards suggest that the OSC should utilize an OC3 signal structure, though some vendors have opted to use 100 megabit Ethernet or another signal format. Unlike the 1550 nm multi-wavelength signal containing client data, the OSC is always terminated at intermediate amplifier sites, where it receives local information before retransmission. The introduction of the ITU-TG 694.1 frequency grid in 2002 has made it easier to integrate Wdm with older but more standard SONET/SDH systems. Wdm wavelengths are positioned in a grid having exactly 100 GHz spacing in optical frequency, with a reference frequency fixed at 193.10 THz. The main grid is placed inside the optical fiber amplifier bandwidth, but can be extended to wider bandwidths. Today's Dwdm systems use 50 GHz or even 25 GHz channel spacing for up to 160 channel operation. Dwdm systems have to maintain more stable wavelength or frequency than those needed for CWDM because of the closer spacing of the wavelengths. Precision temperature control of laser transmitter is required in Dwdm systems to prevent drift off a very narrow frequency window of the order of a few GHz. In addition, since Dwdm provides greater maximum capacity, it tends to be used at a higher level in the communications hierarchy than CWDM, for example on the Internet backbone, and is therefore associated with higher modulation rates, thus creating a smaller market for Dwdm devices with very high performance. These factors of smaller volume and higher performance result in Dwdm systems typically being more expensive than CWDM. Recent innovations in Dwdm transport systems include pluggable and software-tunable transceiver modules capable of operating on 40 or 80 channels. This dramatically reduces the need for discrete spare pluggable modules, when a handful of pluggable devices can handle the full range of wavelengths. Wavelength-converting transponders. At this stage, some details concerning wavelength-converting transponders should be discussed, as this will clarify the role played by current Dwdm technology as an additional optical transport layer. It will also serve to outline the evolution of such systems over the last 10 or so years. As stated above, wavelength-converting transponders served originally to translate the transmit wavelength of a client layer signal into one of the Dwdm system's internal wavelengths in the 1550 nm band. In the mid-1990s, however, wavelength-converting transponders rapidly took on the additional function of signal regeneration. Signal regeneration in transponders quickly evolved through 1R to 2R to 3R and into overhead monitoring multi-bit rate 3R regenerators. These differences are outlined below. 1R, retransmission. Basically, early transponders were garbage in garbage out in that their output was nearly an analog copy of the received optical signal, with little signal cleanup occurring. This limited the reach of early Dwdm systems because the signal had to be handed off to a client layer receiver before the signal deteriorated too far. Signal monitoring was basically confined to optical domain parameters such as received power. 2R, retime and retransmit. Transponders of this type were not very common and utilized a quasi-digital Schmitt triggering method for signal cleanup. Some rudimentary signal quality monitoring was done by such transmitters that basically looked at analog parameters. 3R, retime, retransmit, reshape. 3R transponders were fully digital and normally able to view SONETSDH section layer overhead bytes such as A1 and A2 to determine signal quality health. Many systems will offer 2.5 Gbps transponders, which will normally mean the transponder is able to perform 3R regeneration on OC348 signals, and possibly gigabit Ethernet, and reporting on signal health by monitoring SONETSDH section layer overhead bytes. Many transponders will be able to perform full multi-rate 3R in both directions. Some vendors offer 10 Gbps transponders, which will perform section layer overhead monitoring to all rates up to and including OC192. Multiponder. The multiponder has different names depending on vendor. It essentially performs some relatively simple time division multiplexing of lower rate signals into a higher rate carrier within the system. More recent multiponder designs have absorbed more and more TDM functionality, in some cases obviating the need for traditional SONETSDH transport equipment. Reconfigurable optical add-drop multiplexer. As mentioned above, intermediate optical amplification sites in Dwdm systems may allow for the dropping and adding of certain wavelength channels. In most systems deployed as of August 2006, this is done infrequently, because adding or dropping wavelengths requires manually inserting or replacing wavelength selective cards. This is costly, and in some systems requires that all active traffic be removed from the Dwdm system, because inserting or removing the wavelength-specific cards interrupts the multi-wavelength optical signal. With ROADM, network operators can remotely reconfigure the multiplexer by sending soft commands. The architecture of the ROADM is such that dropping or adding wavelengths does not interrupt the pass-through channels. Numerous technological approaches are utilized for various commercial ROADMs, the trade-off being between cost, optical power, and flexibility. Optical cross-connects. when the network topology is a mesh, where nodes are interconnected by fibers to form an arbitrary graph, an additional fiber interconnection device is needed to route the signals from an input port to the desired output port. These devices are called optical cross-connectors. Various categories of OXCs include electronic, optical, and wavelength selective devices. Enhanced Wdm. Cisco's Enhanced Wdm system combines 1 GB coarse wave-division multiplexing connections using SFPs and GBICs with 10 GB dense wave-division multiplexing connections using XMPAC, X2, or XFP Dwdm modules. These Dwdm connections can either be passive or boosted to allow a longer range for the connection. Transceivers versus transponders. Transceivers are since communication over a single wavelength is one-way, and most practical communication systems require two-way communication, 2 wavelengths will be required. As a result, at each end both a transmitter and a receiver will be required. A combination of a transmitter and a receiver is called a transceiver. It converts an electrical signal to and from an optical signal. There are usually transceiver types based on Wdm technology. Coarse Wdm transceivers, wavelength 1270 nm, 1290 nm, 1310 nm, 1330 nm, 1350 nm, 1370 nm, 1390 nm, 1410 nm, 1430 nm, 1450 nm, 1470 nm, 1490 nm, 1510 nm, 1530 nm, 1550 nm, 1570 nm, 1590 nm, 1610 nm. Dense Wdm transceivers, channel 17 to channel 61 according to ITUT. Transponder. In practice, the signal inputs and outputs will not be electrical but optical instead. This means that in effect we need wavelength converters instead, which is exactly what a transponder is. A transponder can be made up of 2 transceivers placed after each other. The first transceiver converting the 1550 nm optical signal to from an electrical signal, and the second transceiver converting the electrical signal to from an optical signal at the required wavelength. Transponders that don't use an intermediate electrical signal are in development. See also transponders for different functional views on the meaning of optical transponders. Implementations. There are several simulation tools that can be used to design Wdm systems. Popular commercial tools have been developed by Wdm Systems and BPI Systems. See also, code division, multiple access, dark fiber, differential quadrature phase shift keying, IPO-DWDM, multi-wavelength optical networking, optical mesh network, optical transport network, photodiode, polarization mode dispersion, Self-Fock microlens, SFP transceiver, spectrometer, superchannel, time division multiplexing, orbital angular momentum multiplexing. References, ITUT G694.2, Wdm applications, see Wdm wavelength grid ITUT website, ITUT G652, transmission media and optical systems characteristics optical fiber cables ITUT website, ITUT G694.1. Spectral grids for Wdm applications, Dwdm frequency grid ITUT website. Dwdm ITU table, 100 GHz spacing telecomengineering.com, http, www.infiniracumels2html, CWDM SFP transceiver, Optical technology, retrieved March 26, 2013. Dwdm SFP transceiver, Optical technology, retrieved March 26, 2013. Shivaram Murthy C. Gurusamy M. Wdm optical networks, concepts, design, and algorithms, Prentice Hall India, ISBN 81-203-2129-4. Tomlinson, W.J. Lin, C. Optical wavelength division multiplexer for the 1.1.4 micron spectral region, Electronics Letters, Volume 14, May 25, 1978, PA 345 €347 adsubs.harvard.edu, Ishio, H. Manoa, J. Nosu, K. Review and Status of Wavelength Division Multiplexing Technology and Its Application, Journal of Light Wave Technology, Volume 2, Issue 4, August 1984, PA 448 to €463, Chung, Nimke. Nosuke Yoshi. Windsor, Gerard Guest Editorial/Dense Wavelength Division Multiplexing Techniques for High Capacity and Multiple Access Communication Systems, IEEE Journal on Selected Areas in Communications, Volume 8 No. 6, August 1990. Aurora, A. Subramaniam, S. Wavelength Conversion Placement in Wdm Mesh Optical Networks. Photonic Network Communications, Volume 4, No. 2, May 2002. First discussion, O.E. Delang, Wideband Optical Communication Systems, Part 11 Frequency Division Multiplexing HOC. IEEE, Volume 58, PA 1683, October 1970.